Welcome to the second part of my Battle Simulator tutorial series, and I've determined that this series is going to be really short, just 3 videos, and this is going to be by far probably the longest, probably the hardest video, but don't let that deter you because once you finish it, the Battle Simulator was always one of my favorite coding projects. It's a lot of fun to do. But we're going to be doing most of the meat of this project today. We're going to be calculating 2 really big things. One, how to get these soldiers, which are really tiny, how to get them to move towards each other, which is kind of a beast of its own, and then how to actually simulate that battle. And I want to do it all in this video so that the next video is going to be all the fun stuff, like determining how many armies there are and how many, what the stats of the soldiers are, so you can get fun results like that. But let's get that hard part out of the way. So the first thing I'm going to do is Windows. That window's a little bit too small, so I'm going to crank it up 700, 700. I think this is what I was working with earlier. And I'm also going to change soldier size to, well, what is this? Soldier size is a little bit too small. I don't like that. I think it should be maybe 20. There we go. So that's much closer to what it looked like in the thumbnail. And last thing, I really do like the dark red background that you see on the thumbnail, because on the thumbnail, the sea is like all dark red, and I really like that color scheme. So what I'm going to do is I'm going to change my background color to be 130 for the red, but still 00 for green and blue. And you get something like this. And I really like that. I might need to choose a different color for the red soldier since it looks close to the sea, but all in all, this looks way cooler to me. So, those are the little things. Where we left off, our soldiers had no update function here. Or they have an update function, but the update function doesn't do anything. So we're going to actually have it do something now. We're going to have the soldiers calculate the nearest target soldier, and we're going to talk a lot about vectors today. So the first thing we need to do is we need to pass in all the soldiers. We have a whole list of all the soldiers that are in this list right here. And we populated this list using all these 3 for loops here. So what I'm going to do is I'm going to actually pass that list of soldiers in as a parameter for update. And now what we need to do is we need to determine the closest soldier so that we can move towards him. So here's what we're going to do to accomplish that. What I'm going to type is, first we need a target variable. And this is going to be one of the soldiers. I'm going to set it to the first one in the list by default, even though it's probably not correct. We need a closest distance variable. And I'm going to set this to a really high number. And here's what's going to happen. This variable is going to get smaller and smaller and smaller as we keep calculating closer and closer soldiers. So let's say this next soldier we calculate is at 500. Well, then what we can do is the closest distance will now be 500, but then the next one is even closer, 300. So then closest distance will be 300. This variable is going to get smaller and smaller until we finally stop at whatever number is the smallest. That's the point of this variable here. And lastly, we need a distance vector variable. So I'm going to call it distvec, short for distance vector, and it's going to be 2 items, x and y. Let me explain what a vector is. I have a better video on explaining vectors in my slither.io series, so if you want a more in-depth explanation, check that out. But here is my really simplified explanation of that here. So we have, I already drew this out, the Cartesian plane, the y-axis is green, the x-axis is red. So we have soldiers scattered everywhere. We have, and I'm going to add a soldier here, and a soldier, nah, I don't want him here. I want him here, and there's a soldier right here. A vector is simply like an arrow that you add to your position to make it move. So let's say I have the vector, I'm going to type this out, I have the vector 1, 0. What happens if I add 1, 0 to this guy's position here? Let me draw him. Right here. So let's say I have a soldier here. And he's right here, but this is my vector. 1, 0, if I add that to his position, that's going to add 1 to the x, 0 to the y. So as you can tell, that's going to move him in this direction, because that's what the vector 1, 0 does. Here's another very basic example. Maybe instead of 1, 0, what if I added -1 and 1? -1 and 1. Well, what direction is that? Well, that direction, -1 is left and 1 is up. So that's going to give me this vector here. We're pointing to the top left. And when you add a vector to this box's position, so let's say his position was -20, -30, if you add this vector to his position, well, now his position is going to be -21, so he's further to the left, but he's going to be a little bit higher up, so now his y is -29. Vectors are just like these arrows represented by numbers, and you add them to a position to get movement. What is distvec? Because I said distvec is a vector. Distvec is the vector that calculates the direction from one soldier to another. Specifically, if this is the current soldier that's running his update function, and this is the closest soldier, then distvec is going to be the arrow that will get this soldier from here to here on the target position, like that. And how do you calculate a distance vector? You calculate a distance vector like this. I'm going to move them out a little bit more so it's easier to draw. So that's what the vector is. The way you calculate the vector, which I'm going to put in yellow, this is the direction vector. We need to add this vector to his position to make him move here. But how do you calculate it? You calculate that position using this simple formula. The distance vector is your target position minus your starting position, like that. So what is our target position? The position of this soldier. What is our starting position? The position of this soldier who's running the update function. So as you can imagine, if this soldier is at 1010, but this one is at 2020 for sake of simple math, then the distance vector, if you subtract 2020 from 1010, you're going to get 1010, which when you add the vector back to the position, it's going to make this soldier move to the position of that other soldier. So that's just my really brief rundown of vectors, and some of you guys didn't even need that. And again, if you want something a little bit more advanced, you can go to my slither.io video where I explain it more there. So that's enough of that. That's my distance vector, the arrow between our eventual closest soldier and our current soldier. So now what we're going to do is we're going to create a for loop, and we're going to go through all the soldiers in this list for soldier in soldiers. And right away, we have a problem, and this is my other illustration. This is all the soldiers in our list. We have red, 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 green, 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 yellow, yellow, yellow. We don't want to try to track down members of the same team. So what I'm going to do is I'm going to create a team variable as a parameter. We're going to control this in the main game. And I'm going to create the team private variable, set it equal to that parameter. So now we need to actually make a modification from main game. And what I'm going to do is I'm going to set 3 teams. We're going to have red team, and it's going to be 1. Then green team is going to be 2. Yellow team is going to be 3. So we're just giving arbitrary numbers to our teams. So now when we create the red soldiers here, we're going to pass in as a final parameter, since I just now added an extra parameter, we're going to add red team. And then, as you can tell, we're going to add the other teams. Green team will have the green team value, like that. And then yellow team will pass in yellow team. So now we've distinguished all the soldiers by teams. Earlier in the last video, we added all the soldiers to the exact same list, which is going to be more efficient for reasons we'll see later, but it does create a problem. Like, we didn't use 3 lists, one for red, one for green, one for yellow. We packed them all in the same list. So we need to give them numbers that show us that these guys are on the same team, so we don't try to fight them. That's how that's going to work there. So now that we have a team, let's go back to soldier. And if we are looking, if the soldier that we're currently looking at, if soldier If his team is the exact same as the current soldier's team, just so you don't get confused, soldier in the for loop is simply the soldier we're currently looking at as we're iterating through all the soldiers. And then team or self is the soldier running this function right now. And I hope that's not confusing. So if the teams are the same, what we're going to do is continue. We're going to skip and look at the next soldier because we do not want to look at the same soldiers of the same team. But now we found a soldier. So if this doesn't run, we found a soldier who has the same or who has a different team. So now let's get the distance vector. Dist_vec in the x, which is going to be the first item in the list, is equal to, like I said earlier, target minus start. So what is our target? Well, the soldier we're looking at, dot hitbox dot x minus, and then what is our position? Self dot hitbox dot x. So now that's our distance vector for the x. Let's get it for the y. Really easy. Soldier dot hitbox dot y minus self dot hitbox dot y, like that. So we've calculated that arrow. We know exactly what direction that this soldier needs to move to reach the other soldier. But we don't know if it's the closest. We need to see the distance. What is the actual distance? We have the arrow now, but how long is that arrow? That is the distance. How do you calculate the distance? Well, if you know the Pythagorean theorem, you'll already know this, but if not, you can just memorize it. The distance of a vector is simply its x, or it's the square root of its x squared plus its y squared, like that. So what for us, that's just going to be the square root of the dist_vec 0 squared, and then minus the dist_vec y squared, like that. So that's how you get the distance of a vector. And for you math geeks, you can tell this is just a adaptation of the Pythagorean theorem, or just a distance formula. So we have, if that formula doesn't make full sense, that's fine. You can just memorize it. It's right here. So distance is going to be the square root, which is the same as raising something to the half power. So I'm going to do that. This is the exponential operator here. So what is it? Dist_vec x squared. And then we're going to add dist_vec y squared. So we took the x squared plus the y squared, and we took the square root of all of it together. That's what this part does. And now we know how long that arrow is here. So now let's just do a check. If that distance is less than our closest distance, then we should set the target soldier to be this soldier that we just found to be closer, and our closest distance is going to be distance. And you can tell that this is going to make closest distance gradually smaller and smaller. If distance is 500, well, 500 is less than 20,000, so we reset target, reset closest distance, and then so on. If the next soldier is only 100 pixels away, 100 is less than 500, so target is going to be whatever that soldier was, closest distance is now going to be just 100. So now this for loop, as long as it keeps running, it's eventually going to give us whoever our closest target is and whatever our closest distance is once it is run long enough. So now we're outside the for loop. And let's do a few checks first. Let's make sure that the closest distance isn't 0 for just something we're about to do. If closest distance, we're about to divide the dist_vec by 0, so by closest distance. So we want to make sure it's not 0. If the closest distance is 0, or I'm going to add another condition. Let's say there is just one soldier in this whole list. After the whole battle runs, there's just one surviving soldier. Well, target is equal to soldier 0. Well, that means that, well, let me show you. Here's our list of soldiers. Imagine every other soldier has died except this green one. So now the length of this list is just 1. This green one is the last one left. But this green one's going to keep updating. So he's going to call his update function. It's going to start here, and the green's going to say, hey, my target is equal to the first soldier, which is himself. So he just set himself as his own target. And now what's going to happen is, since they're the same team, this is going to skip, and what happens here is target stays as himself. So we're just going to add, if that didn't make full sense, that's fine. We're just going to add this condition here. We're going to make sure that the target is not ourselves. So if target is equal to the self, or if the closest distance is equal to 0, what we're going to do is we're going to return. We don't want to do anything else. We're not going to move. We're not going to do anything. But if we made it this far, if we made it through the full for loop, and the target is not the same as the soldier, now we can do the movement calculation. So we need to recalculate the distance vector. The distance vector is, now that we have a target, we can say target dot hitbox dot x minus self dot hitbox dot y, or x. Don't do that. Then distvec for the y is target dot hitbox dot y minus self dot hitbox dot y. So we did this earlier, except now we actually know which soldier is the closest, instead of just doing every soldier and checking every single one to see. So now we know which soldier is the closest. Now we're calculating the true distance vector, because what we are doing earlier is checking the distance of every soldier. So if I had a soldier here and a soldier here, what we did is we calculated this vector and this vector and this vector. Now we know this one's the shortest. So now we recalculated it. And now what we're going to do, and let me explain something about vectors. So let's say, again, let's just pretend that this is our distance vector. This is our player, or not our player, but the soldier that's currently checking. This is the target. Now the distvec we already determined to be 10, 10. But like I said earlier, you add vectors to your positions to make movement. If we add 10, 10 to this soldier here, he's going to move right on top of the, oh, let me get a bigger selection. He's going to move directly on top of the target. If we add the dist vector in its entirety, we're going to teleport this soldier from here to here. And that's going to look really bad, having all our soldiers teleport to each other and then instantly start fighting. What we want is we want to keep this exact same direction here, but instead we want to, so let me erase that. We want to keep that same direction, that same distance vector, but we want to shorten it so it's not quite as long. We want, let me select the line. What we want is a shorter vector with the exact same direction. So like instead of your distvec being 10, 10, what if we made it something simple like 1, 1? So here's how we're going to shorten the vector. We're actually going to normalize it, which means we're going to divide it by its length. So I'm going to take the x, which is, in our arbitrary example, 10, and I'm going to divide equals, by closest distance. I'm going to do the same for the y. The distance vector in the y divided by equals closest distance. So what I did here is I divided the x and the y by the length of the vector, which is closest distance, and this is called normalizing the vector, but if you don't really care for that terminology, all we did is we shortened the vector. We shortened the vector. And we're almost done with this part. Now the vector is short, but it's now too short for a reason we'll see later. So now I'm going to add a speed multiplier and set it to 2. And now I'm going to multiply the x and the y by 2. So times equals self.speed, distvec 1 times equals self.speed. And lastly, distance vector is simply a vector, so we can add it to our position to get movement. Self.hitbox.x plus equals distance vector 0 self.hitbox.y plus equals distance vector 1. And if this part was probably really confusing, like I said, we shrink the vector so that we are not teleporting this soldier from here to here. We want gradual movement. We want, say, 10 steps. We want to see the soldier move 10 different steps before he reaches the target instead of just jumping there. That's why we divided our vector. Now we multiplied it by a little bit because when you divide a vector by its distance, you're going to get fraction values like 0.1 and then 0.9, and it's going to be less than 1. And you can't move a pixel by a fraction. So we need something that's at least 1 or above. So that's why I multiplied it by 2. And we'll see more of that in a second. So then we add that vector back to the hitbox. I'm going to run this. And now let's just get rid of all the errors that I made. First one is we now need soldiers as a parameter. So now let's provide soldiers. When we call the soldier.update, let's give it self.soldiers as a parameter. Let's see what else I did. And it worked. Let's run it again. So they're chasing each other, but you notice they still keep moving. Let me run it one more time. They chase each other and they kind of converge on the same spots, but they keep moving. Why do they keep moving? Well, because we told the soldier, you do not, the way the soldier works is we are just waiting for the closest distance. We're waiting for the distance between the soldier and his target to be 0. That's the only thing that's going to make us return. So if the closest soldier has the exact same position as the soldier that's currently checking, then closest distance is 0, we're going to return. But basically, that's never going to happen. We're never going to have exactly 0 for the distance between two soldiers. We're never going to have one soldier perfectly on top of the other like that. So what we're going to do instead, and that's why they're always going to be moving forever and ever. So what we're going to do instead is we're going to allow a little bit of leniency. We're going to return the function and not move the soldier here, or excuse me, here, if that closest distance is less than 10. So if the distance between one soldier and another is 5, we're going to say good enough, don't even bother moving. And now what happens is the soldiers will reach each other and they'll stop moving because the distance is close enough. They're not trying to get directly on top of each other, but the distance is close enough there. And now we have to where the soldiers are stopping. And I'm going to run it again. And that was a really big portion of this program. Good job getting this far because this was probably the heaviest in the math. Don't be discouraged if not all of this made sense. You can rewatch the video, watch my vector video, or simply memorize because that's how you learn coding. Sometimes you just got to memorize things before they come to make sense later. I'm pretty sure I memorized this at one point. So now the soldiers are moving, and that was the hardest part about this video, just getting them to move. The next 2 parts are going to be easier. So here's what we're going to do. Let's move all this into a function called calculate direction, since all this is doing is calculating the direction that the soldier needs to move. So define calculate direction, and we're going to, I'm just going to copy and oops, I separated that. This needs to be in the update. But everything else I'm going to move inside of calculate direction. Calculate direction needs the soldiers in the list. So now we're going to call self.calculate direction with soldiers. There we go. So it should run the exact same. And I made a mistake somewhere along the way. What did I do? What did I do? Made a mistake somewhere here. And here's what we need to do. So distance vector we calculated in this function that we just created, but as soon as the function ends, this variable gets destroyed, so we need to save it. Otherwise, it means nothing in our update function. So I'm going to create a velocity variable, and it's going to be, I'm just going to set it as 0, 0 to begin with. But now what we're going to do is we're going to say, after we do all this work and get the direction, we're just going to set our velocity to the distance vector. Velocity to the distance vector, like that. Because velocity is also a vector. Really, that's just a way you think of these arrows. Like this arrow we did, -1, 1, that's a velocity vector. We are adding it to the position to get movement. Same with this, a 1, 1 for this vector over here. That's velocity. So we're going to set our velocity to the distance vector that we spent all this time calculating. And now instead of adding the distance vector, we're going to add self dot velocity, and I keep spelling it wrong, velocity 0, there we go, self dot velocity 1, and now we're not going to get that error, and we get the exact same result as before, except now they're moving again. Why are they moving again? Well, because now we are allowing movement even when the closest distance is less than 10. So what we need to do is we need to not just return the function, we need to also reset the velocity. So if our target, if any one of these conditions is true, if the distance between our target and ourself is 0, if the closest distance, if that distance is simply less than 10, or if the target that we're looking at is ourself, we need to not just exit the function. Now we need to reset velocity to 0 because this code up here is happening either way. So we need to make sure velocity is 0 for when those soldiers are only 10 pixels or less apart. So when I run this, now they're going to converge again, just on simple spots. So that's good, that's done. It's the exact same thing we had before, but we have a slightly better result. Now what we need to do is we're going to make another function where we're going to fight the battles. So what we're going to do is, let me create that, define fight battle, and this needs a target. I'm going to call it an enemy. This needs a enemy parameter. This is where we're going to simulate that actual fight, that battle, which is going to be a lot easier than what we just did. And so what we'll do is we got to make some changes to calculate direction in order to do this, because what is our enemy? Target. Well, target is inside the calculate direction function. So, and it's not going to get saved. So what we should do is, if one of these conditions is true, we'll return false to tell our update function that we have no target. But otherwise, at the end, we're going to return the target. Now, let's take that target. Target is equal to self.calculate direction. And if target is not equal to false, then we should fight battle and fight that soldier. If we have a valid target, then we're going to pass in target. So I probably should have modified that calculate direction function before we started fight battle, but all we did, we have this target that we just calculated. This target's a soldier, but the soldier variable is inside the update function. We need to return that variable so that we can use it in our fight battle function here as a parameter. But of course, we're going to use false if there is no valid target, which we're going to check here. One more thing, we shouldn't just fight just because there is a target. We need to make sure that these soldiers are actually making contact. Soldiers on two opposite sides of the map should not be able to fight. So let's check if the two soldier boxes are touching. So I'm going to add another condition. If, and what's cool is Pygame has a really good function built in, which lets you see if two rectangles, which is what our hitboxes are, if our two rectangle variables are touching. So I'm going to type if self.hitbox.collide rect, that's our function. It takes another rectangle as an argument, so target.hitbox. So altogether, hitbox is our rectangle, our hitbox rectangle, Pygame rect object. It has a function called collide rect, which takes another rectangle as an argument. And this function will return true if this hitbox is touching this hitbox. Really easy to use and nice that it's built in. So if the result of that function is true, if there is a collision and there is a valid target, then we should fight the battle. Let's pick it up with the fight battle. This is going to be pretty easy. I'm just going to create a while loop, a very simple while loop. And what we're going to do here is we're going to simulate the battle and then return the function when we are done with the battle. We need an attack and a health because the way this is going to work is two soldiers are going to generate a random attack and then subtract that random attack from the other soldier's health. So let's get some attack variables here. And I'm going to separate some of these. There we go. So I'm going to think of these variables, self and velocity and texture and hitboxes are all our essential variables. Here's our game stuff. The team self.health is equal to health. So I'm going to add another parameter because I want main game to control this. And then self.attack. And I should call this max attack for a reason we'll see in a second. And I'm going to add a attack parameter here. So let's go in main game, and since this video is getting pretty long, I'm not going to bother creating more constants here. What I'm going to do is I'm just going to add those parameters. Red team, they get 100 health and their maximum possible attack is 30. Green team, same thing, 100 health and maximum attack of 30. So let's go back to soldier. Now let's generate the attack for this soldier, the soldier who's running his update function. Attack is equal to random.randint, that will give you a random integer between these two arguments, 0 and self.maxAttack. So, and let's make sure we have random imported so I can use that random function. So this is our attack for the current soldier that is updating. His attack is a random number between 0 and his maximum attack, which we just set to 30. So he can have a really weak attack or a really strong attack. The enemy has the same chances. The enemy attack is going to be random.randint 0 to enemy.maxAttack. So we have two random attacks. Now we need to subtract those attacks from the health. And we're going to say self.health minus equals attack. And we're going to say enemy.health minus equals attack. Or not attack. I made a mistake here. So we're going to subtract the enemy attack from the current soldier's health. And we're going to attack the current soldier's attack. We're going to subtract the current soldier's attack from the enemy's health. So it's opposites, as you can probably see. And you can probably tell I've been recording too long, but this is almost done. So we have this. Now what we should do is we need to run this while loop repeatedly. They're going to keep attacking each other, keep generating random attacks, but we need to stop when somebody dies. So if either the current soldier's health is less than or equal to 0, or the enemy's health is less than or equal to 0. If either one of them die, what we're going to do is return. That's going to bring us out of this for loop and this while loop, and this function will end. So what we're doing here is we use this calculate direction function to find the nearest soldier, and more importantly, to just get that proper velocity vector so we know where to move. And then if there is a valid target and the two soldiers are touching, then we can fight the battle, and all we do here is generate random numbers and subtract them from each other. And as I messed up saying earlier, the current soldier, you subtract the enemy's attack. The enemy's health, you attack the current soldier's attack. It's opposites. And now what I'm going to do is I'm going to run this, except, let me make one more change, because this doesn't do anything. Once health is 0, we don't actually delete the soldier. So let's delete the soldier. What we're going to say is, in our update function, we're going to say, if at any point our health gets to be less than or equal to 0, we're going to return true and tell the main game, hey, this soldier needs to be deleted. Otherwise, we're going to keep going and return false so that this soldier lives to fight another day. So let's add that to main game. So let me scroll down to our update. Here we're updating all the soldiers. And I hope when I'm saying current soldier, I hope that hasn't been confusing. The current soldier, every soldier in our list is calling the update function. So when I say current soldier, I just mean whichever soldier is running his update function at that moment. And the enemies is typically just another soldier in that list who's not running their update function at the moment. So here are all our soldiers. What we're going to do is now that we're returning values from our update function, we can say if the result of the soldier update function is true, then what we can do is remove the soldier, delete it. So self.soldiers.remove which soldier? This soldier who just died. I'm going to run it, and fingers crossed, and I made some mistakes. Here's the first mistake. I forgot to have self.fightBattle. So let me add that, self.fightBattle. And now they are fighting and killing each other. Man, let's see that again. They're moving, the battle goes really quickly and they move really quickly, but at the end there is just one winner here. And notice he stays still because again, in our calculate direction function, if there's only one soldier left in the list, that means the target is the same as the soldier that's running the check. So we set velocity to 0. But now you are done with most of this video, in fact, or most of this tutorial. Let's just stress test this. Let's add a little bit more soldiers. So let's make it 30 on every team. And now when you run that, you get a lot more action, but it's still really fast. So now would be a good time to take a break, maybe if you need it, because you now have a working battle simulator, and good for you. You can now spend time on your own just stress testing this program, adding more and more soldiers like that. I'm going to make it 100 per team, and you're going to get cool results. But what I want to fix, what I'm going to spend the last part of this video fixing, is them moving so fast. So if you need a break, now would be a good time to take it because this is an excellent stopping point. And really, this works, but I don't want them moving this fast. So let's fix them moving so fast. Why are they moving so fast? Well, you might think it's because we're multiplying our vector by 2. Remember earlier we shrunk down the vector to where we normalized it to make it really small, and I told you that was, quote, too small, whatever the heck that means. So then we multiplied it back by 2. So you might think, maybe we shouldn't multiply the distance vector by 2. Where do we do that? Calculate direction, right here. We took our distance vector, we divided it by its length, which is normalizing, then we multiplied it by 2. Let's see what happens when I take this out. When I run the program, notice there's a lot of soldiers that actually stopped moving and then started moving again. Do you see how they're all just moving all janky? We'll see it again. There's a few soldiers that just stop moving, like these 2 red ones here, and then they start moving again. Why is that happening? Let's see. Let's print just the dist vector for the x. Let's just print that. And every frame, we get a value that is almost every frame, we get something that's less than 1. This means pixels. This is a value in pixels that we're going to try to add to our hitbox's position. You cannot, in Pygame, move an object by half a pixel, or maybe 0.9 pixels, or negative 0.3 pixels. That does not work. But notice some of these guys were able to move directly in one direction as 1, or negative 1. You can move in just one, you can move 1 pixel, but you cannot move a fraction of a pixel, which is why some soldiers were not able to move at all because their calculated direction was this fraction. So when we multiplied by 2, check out what happens now. When we multiply by 2, we fix that, and now almost all these values are greater than 1. And so now we can have valid movement. Pygame will just round this down. So like this is negative 0.99. We don't want a fraction of a pixel, so Pygame rounds this down to just negative 1. So now when we multiply by speed, now all the soldiers are able to move, but they don't move, or they move way too fast. So maybe we should change speed to where we want it to be greater than 1, but less than 2, so maybe 0.1. But you'll see, and I've tested this, you'll see that they still move far too fast. Even at 0. I mean, even at 1.1. But any less than 1, and we're going to get half pixels, and we're not going to get any movement. So how do we fix this problem? What we need to do is actually keep track of how far the soldier has tried to move, and once it has tried to move in any direction more than 1 pixel, then we allow movement. Here's what I mean by that. I'm going to create two more variables, self.xDistance and self.yDistance. So this is just how far in the x and y axis the soldier has attempted to move. Again, when you try to add 0.6 to his x position, he won't move. But that 0.6 we're going to save in x distance. So this will be 0.6. And now, let's say the soldier moves again, tries to move 0.6 again. Well, now this is going to be 1.2, which is a valid movement because that's 1 pixel. So what we're going to do is we're going to use these variables to keep track and add up how far they move. And once they move to a value above 1, then this is what we're going to add to the hitbox's position. So we're still moving in the exact same direction, but our movement is delayed until we can add up something greater than 1. So I hope that's not confusing. Let's get into it. So here, we're not going to do this anymore. We're going to do something a little bit more advanced. We're going to say self.xDistance is going to be, we're going to add the velocity, the x velocity. And we're going to do the same with y. We're going to simply add the y velocity. Like that. There we go. And now what we're going to do is we're going to check. Keep in mind, velocity can be a negative or a positive number. So what I'm going to do is I'm going to just check the absolute value. If math.fabs, that's the absolute value function. If the absolute value of the total x distance that the soldier tried to move is greater than or equal to 1, then let's add that x distance to the hitbox. Self.hitbox.x plus equals self.xDistance. So again, I'm using absolute value here because velocity can be a negative or a positive number. So we don't want to, so that would mess up this comparison here. But when we're done, if the soldier is trying to move to the left, that's a negative number. So we can't use absolute value here, but we have to use it up here. So if the total distance that soldier has tried to move is greater than 1, then we're going to add that position to the hitbox, and we're going to reset the x distance. X distance is going to be 0. And for sake of time, I'm just going to copy this and paste it for the y. I'm going to change this to y, hitbox.y, y distance, y distance. So again, I hope that wasn't confusing. All we're doing is we're now, instead of immediately trying to move the soldier, we're delaying his movement. We're waiting for his total movement to reach above 1, and then we allow the soldier to move. Because if we just try to add, like 0.1 to his position, that's not going to do anything. But if we try to add this 10 times, well, that's going to give you 1, and we can add 1 to his position. So this is going to just basically allow us to slow the soldier virtually as slow as we want, and still allow these fraction pixels there. So I'm going to run the program, and now we're at 0.1.1 for the speed. I'm going to change this to 0.1 because this is allowed. Even though this is a really small number, we are adding the x distance up until it's greater than 1. So notice now we have, well, unless I make a mistake, like forgetting to import the math function so that we can use math.fabs. But now when I play it, notice that now we have full control of their speed. Watch how slow they are now moving. They are no longer out of control. And in fact, I could make this even smaller. I could make it 0.05 and make it twice as slow. All that means is the soldiers have to wait a little bit longer for this x distance to add up to something greater than 1, but they're still able to move. So we still preserve their exact direction, but we just delay when they can move so we don't try to move them by a fraction of a pixel. That's why we're waiting for 1. And you have reached the end of this video. That was a really long video, and I didn't mean it to be that long, but like I said at the beginning, this video is the vast majority of the work behind this battle simulator. And now enjoy your program. What I want you to do is go up here and just change different values, add different, have fun with this. Try having teams at 200, make the teams different strengths. So red team, I'm going to give double the health and maybe just 10 for the maximum attack. So they're really hardy but have really weak attacks. Green will stay the same. We're going to make yellow soldiers have a health of 50 but a maximum attack of 100. Have fun. Change these values and click the play button and just see what you get here. And actually, let's turn up that speed now that I was just doing this for illustration. 0.1 has been my favorite so far. Oh, and X distance should not start out as 1.2. It should start out as 0. That was a mistake I made. So now just have fun. It's a little laggy, but as the soldiers die off, it's getting better. And just run your program and see who wins. So I actually am curious to see who wins. And there's still red soldiers here. They're just really hard to see. And it looks like yellow just totally demolished everybody just because of their high attack value. There's some green hanging out down here, green and red over here. And they're probably going to die in just a second. He's almost got him. And it's over. And they all stop moving because the only people left are the same people on their own team. So good job making it this far in my video, and most of the battle simulator is done. I'm going to spend the next video on simply fine-tuning the battle simulator, adding cool user interface stuff like adding how many armies we have, and being able to customize these stats for the soldiers. Where is it? These stats while the game is running. So I'm really looking forward to the next video. Good job getting through all the hard work of this one.